We live in a world connected through technology and people. But for some of us, it's not always easy to connect.
Many in the deaf community say they've been forced to stay at home because they become frustrated and anxious when they can't understand others properly.
With over 5% of the world population being affected by disabling hearing loss, only 1% knows how to use sign language. This figure is mind-numbing. The existing solutions that currently exist include Linguano. This app provides a colorful UI for users to learn from, including different demonstration videos. This is the same with the ASL app as well as the Pocket Sign app. But all three of these miss one key feature, and that is for the users to track their progress, to track if they're actually learning the sign correctly. Another solution might be one-on-one tutoring. Again, this requires high engagement and can be pricey at times. Introducing mySign. mySign relies on the potential of a convolutional neural network to provide an easy-to-use interface for all individuals. In the app, the users are able to select any category they want to learn from. For example, they click on alphabets. They're able to scroll through the 26 letters of the alphabet, each by pressing Got It as they move through the letters, or they can press the previous button to go backwards. In each screen, they're able to see the sign that they need to present, as well as tips on how they could achieve it. They could do the same with numbers. Click on each number to go ahead, and then using the previous button to go backwards. Again, the tips are shown for each sign. Next, if the user wishes to test their knowledge, they're able to do so by clicking on the test icon at the bottom right. Once clicked, they're presented the alphabets, the first letter being A. If the user doesn't want to test the letter A, they can scroll to the next one by clicking on the right arrow. But if they do want to test A, they can click on take a picture and they're redirected to the camera screen. Over there, the user is able to present the sign asked for. Once the picture is taken, the image is classified and the result is displayed. If the user is right, the result is displayed in a green box. If the user was to test the letter A but does the sign B, it's going to say that the alphabet sign is B but it's wrong, since it's displayed in a red box. To achieve this product, TensorFlow was used in parallel with React Native. TensorFlow was used to train a custom image recognition model, which was then implemented in the React Native app. To obtain a custom image recognition model, a 4-layer convolutional neural network was trained. As you can see, each layer has a different number of filters being used. For example, the first one has a total of 32 filters, and then we're using max pooling to reduce the spatial dimension of the output volume. The second layer uses 64, the third using 128, and the fourth one using 256. Then, flattening is used just to flatten the input, and then a dense layer is applied. A dense layer is simply a layer of neurons in which each neuron receives input from all the neurons of the previous layers, therefore calling it a dense layer. Dense layer is used to classify an image based on the output from the convolutional layers. Lastly, softmax is applied, which converts a vector of values to a probability distribution. As optimizer for this model, Atom was used. This model showed 97.5% accuracy on testing data, which was done through Colab. But after this, 1,300 images were taken through the application, and classification on those images showed 98.9% accuracy. Moving on to the implementation of the app. When the user opens the app, the first page they see is the learning page, which is seen right here on the right. The user can select any category they want to learn from, and this is implemented here in the const function, which is called learn page. It takes the navigation as a parameter, as we have to use the navigation from the user to see which category they have selected. For example, if the alphabet is clicked, which is shown over here, which is the learn button, the user is redirected to the learn ASL page. This is the learn ASL page. Over here, the user is able to learn from the 26 letters of the alphabet. For example, over here you can see a screenshot of the letter A. The users are given tips which are shown right here, of how to make the sign. Now when the user wishes on to proceed to the next alphabet, they can click got it. And as you can see, the button takes as an action and takes in the parameter learn B. And learn B is this class over here, which is called learn B, which takes navigation as an argument again. It's the same implementation, where the users have been given tips on how to learn and can move on to the next or the previous alphabet. Now when the user wishes to test their knowledge, they're able to do so using this test icon at the bottom right. This test icon is implemented using a bottom tab navigator, which over here takes as a component the learning page as well as the test page. And when the test page is clicked, they're redirected to the test page, which you can see over here the implementation for. In the test page, the user is able to select the alphabet they would like to test. For example, in this case, it's the letter A. Now when the user is ready to test their knowledge, they're able to click on take a picture. When take a picture is clicked, the camera class is called and the location of where the user is clicking from sent as an argument. In the camera class, we have initialized a stack navigator for the navigation and a mapping of all the different classes that could possibly take place. This is a page the user sees when they have clicked on the camera page. As you can see, there's a specified location in which the user is meant to place their hand. Over here, I've set different states. Over here, setting the stage for image processing, the alphabet being presented, the user permissions if the user has given permission for us to even use their camera, and the prediction probability. First over here, I check whether the user has granted permission to use the camera. If given permission, the user is able to see this page. In this page, when the user clicks on image capture, an image capture function is called. In this image capture function, the set of image processing is set to true. The reason for this being set to true is we have created a model class over here which is only shown when the image is being processing. This function image capturing calls the image prediction and sends the image taken as an argument. In the image prediction processing class, the image is first resized using the image resizing function. And now you may wonder where this image resizing function is from. This image resizing function was created in the prediction support folder called image formatting support. Over here, the image is resized suited to the model. First, taking the width and height of the user's device and using it to crop the image to the appropriate size. Then converting the image into a JPEG and sending it back. Once received, the model is fetched. Now you may wonder where the model is fetched from. This model is fetched from the tensor predictor file. This file stores the model locally over here, as you can see, and then over here you can see the fetch class. This fetch class just loads the model, and if the model is not loaded correctly, an error is shown. Over here you can see another class which you will see shortly in the camera class is the convert image to tensor. Over here, the image is decoded using the base64 binary file, which is util file, and then the image is reshaped. And if the image cannot be converted to tensor, an error is thrown. Next, getting the prediction. Over here, it takes the model and the tensor as a parameter and uses this to predict the alphabet shown. Once predicted, the prediction is returned. If not, an error is thrown. Now let's go back to the camera class. So over here, as you can see, the image is first converted to tensor and then the prediction is calculated. Once the prediction is calculated, the highest prediction is stored and then the highest prediction is then mapped. Over here, as you can see, an if statement is used to see which color to be shown. So if the user is right, a green color is shown, and if the user is wrong, a red box is shown indicating the user is wrong. Overall, Overall, this project deemed a success. I was successfully able to implement a machine learning model into a React Native application with very limited resources to go off of. And having achieved such a high accuracy in the image classification model is something I'll always be proud of, and I hope to launch this app in the near future.